In the end, why Lagrange was said in the picture.
Why Lagrange was said? Oh, yeah, because nobody bought his book because there were no pictures in it. Yeah, there was a good question from the audience. Before the break I said Lagrange looks so sad in the picture. And then why did he look so sad? And well, probably because nobody bought his book, because there were no pictures in it. I don't know. The other thing is, of course, all the names, and it is sort of interesting to see all the names he had. So yes, it was Joseph, so the M was Monsieur, and Joseph Louis, or born Giuseppe Luigi Lagrangia. And of course everybody thinks Lagrange is from Paris, but of course he's not, he's from Torino. He's an Italian, so therefore suddenly the name Turin ends up in the book. Yeah, and the sad picture, I don't know. I know nothing much. I don't know so much about his life. What is interesting is here that you see all the connections, and the connection is in 1766 on recommendation of Leonhard Euler, nice picture of Leonhard, and the French Monsieur d'Alembert. Lagrange succeeded Euler as the director of mathematics at the Preußen Academy in Berlin, Prussia. So therefore the name Berlin was there. But you see the interconnection. Newton, he uses Newton's equations, he uses D'Alembert forces, he uses of course the Euler equations also, and then he is sort of the one who brings it all together and makes a nice algebraic framework to do the calculation of the equation of motion. A really revolutionary step in mechanics in that sense. Okie dokie. Back to today. Yeah, that's my mistake. Microphone is running. Let me check again if everything here is running. Yeah. Okie doke. Now, so we had the equation of motion, then via an integral with respect to time we go up to one level to energy. And what is the usefulness of that? And let's do an example. So it is useful to think in this system of energy and energy conservation, especially that, like the kinetic plus potential energy is like an invariant of the system. It will not change. It's constant, and that we can use. And also the old warlords used that in the old days. I guess. I hope. I know. I don't know. War is always popping up. For some reason, mechanics and war are connected. So imagine that you are lord of the manor, right? And you have to defend your manor. So what do you build? You have a pond here, and then you have a nice bridge, and then people cannot come to your castle. But one day you see the trees coming towards you. They slowly move into you, like the forest is moving towards your castle. It's a famous old story by Shakespeare, I guess. And then you're in your castle and you're worried, so what do? You shoot down the trees. And how do you do that? You have a cannon for that, a big cannon. And you put an amount of powder, black powder in it. And then you shoot off a cannonball with some velocity. And let's call that V0. And of course you know exactly the velocity because you know the mass of the ball, you know the amount of black powder, and you can do your math. You also know the height of your castle with respect to the trees. We call that h. Oh, that's not a nice h. And of course you also know your mechanics. And the big question is, of course, will I hit my trees with a velocity that is large enough to kill the trees, right? Or the enemy. Now, how does the ball go? Well, like this, or it doesn't really matter how the ball will go, but in the end it will end up here. And the path, you don't know, but even more, it's not interesting. Because you know an invariant. And the invariant is that the kinetic energy plus the potential energy should be constant. Let alone there's some drag and some, well, we forget about that. So we say, oh yeah, kinetic energy plus V should be constant. Or in other words, let's call this stage 0 and this is stage 1. So I know T0 plus V0 equals T1 plus V1. Okay. What is the kinetic energy at 0? That's 1/2 mv0 squared, right? And the potential energy, mgh, that's with respect to some level. And then at T1 we have 1/2 mv1 squared plus 0, because this is like the 0 level of your potential energy. Then, given that how high your castle is and how the velocity, your muscle velocity, you can calculate from this V1 equals square root of V0 squared plus 2gh, something like that, yeah. And you solved your problem without even bothering about what is exactly the trajectory of your bullet, right? So, in some problems in mechanics, it can be useful to use these invariants. Okay, now we're no warlords, we do rigid body dynamics, so let's assume we have a system of rigid bodies, and in our system of rigid bodies we have coordinates and speed, so we assume we have these speeds, x dot 1, y dot 1, phi dot 1, etc. until x dot n, y dot n, phi dot n, as many bodies as we have. And then connected with that speed is of course the mass of the bodies and the kinetic energy. So we have some mass matrix, Mij, and that's usually like in our case a diagonal matrix with M1, M1, I1, and then etc. to Mn, Mn, In, all at the central mass. Then with these things I can express for that system the kinetic energy. It's just a number, 7.845 or something like that. 1/2 x dot I Mij x dot t. So this is the kinetic energy of the system. And what is the potential energy of the system? Well, we had this definition that the forces, the potential energy was actually defined by Fi is by definition this partial, I make a mistake, sorry. Partial derivative with a minus sign in front of it. That's actually the definition of the potential energy. Or you could also say, in other words, the potential energy is minus the integral of force times this dx. And that's a definition of the thing. Now we have our potential energy, we have our kinetic energy. How do you get from this T and V back to my Newton Euler equations of motion? Because in the end that is what we want. And we went up one level to energy, but if we have these energy expressions, can we then go back to our equations of motion? And it's of course super simple. First of all, the forces, well, those are simple, right? We already have that definition. If we have the potential energy, then we can find the individual forces is minus dv over dxi. So those are the forces. How do we find mass times acceleration? Well, if we differentiate the kinetic energy to the speed, then what do we get? We get this mass. I now just work with scalar type of things, right? To make it not too complex. Mass times speed. If we differentiate with respect to speed, we get mass times speed. If we then differentiate that guy with respect to time, then we get, well, you would say m dot, but we do always do mass is constant. Constant. If you want to do variable mass systems, we have to do a little bit other tricks with impulse and momentum and so on. So that's m times x double dot I. We for now we just consider constant mass systems. So now I have my acceleration term, I have my force term, and again I get my Newtonian equation by saying, oh, apparently if I do this, if I take the derivative of the kinetic energy which was differentiated with respect to the velocities with respect to time, plus I take the potential energy differentiated with respect to the coordinates, then that should be equal to, I tend to write Fi here because not all forces can be captured into potential energy. So those are non-potential energy forces. So all the other forces which are not in the potential energy, I write on the right hand side. And these are just our equations of motion. Equations of motion. So if we go up to the level of energy, and then by this rule we have to go down again. Now, why this strange differentiation? Here it's directly with respect to this force with this coordinate. They coincide. I mean, those are identical, but here it's a bit of a trick you have to do. And may I remember how we got our energy equation here? We also did that by changing the variable. So here we stayed we went to dx, and here we suddenly integrate with respect to speed. So therefore we have to first do that trick like differentiate with speed and then with respect to time. That's the short explanation why we finally end up with this guy here. But anyway, these are the equations of motion, and you just get mass times acceleration minus forces, all the non-potential forces. Now you would say, well, that doesn't help me much. I go up to the energy level and I go down again, and then I'm back where I started. Looks like you're doing a homework problem and you cannot find a solution. So what's going on? Well, now comes the big trick. Instead of using using these COM coordinates xi, I want to use generalized coordinates. And generalized coordinates, I usually tend to write them with qj. You already saw that a little bit in the beginning. I said with the alpha, beta, and the gamma, I call those qj. So let's take an example for that. Let's take our double pendulum thing, and I'm going to choose. So these are this is x and y and phi, and this is the ground. And then this was body 1 and this was body 2. Now I choose two coordinates, alpha and this relative angle beta. And I do that on purpose to say it's a generalized coordinate. It's not an absolute angle of that body with respect to something, but it's a relative angle. So I'm going to choose for this case alpha and beta as my generalized coordinates. And remember, all my CM coordinates are x1, y1, phi1, x2, y2, phi2. So I have these six coordinates, and apparently, since we have 2 degrees of freedom, I can describe them with these two generalized coordinates. However, my goal is to have an equation of motion in qj, in q dot j, and q double dot j, right? That is my goal, because those coordinates and their time derivatives describe our system uniquely. How do we do that? Well, first of all, we have to realize that with these new coordinates, I also have new forces. So not only do we have generalized coordinates, we also have generalized forces. So the generalized forces are, capital Qj And in our case, it's a torque at alpha and a torque at beta. Two torques, two angles, two torques. And how do they operate? Well, so there's a torque here, T alpha, on body 1, and there's a action-reaction torque, T alpha, on the ground here. Likewise, there's a torque, T beta, acting from body 1 on body 2, and there's an action-reaction torque here for the T beta. Okay, so we now have generalized coordinates, we have generalized forces, and now we're going to connect everything. Because, remember the mechanical power definition for our system? There was P equals Fi x dot I, summation over all the i's. So that was defined in our generalized coordinates. But likewise, you can also say, oh yeah, but in our CM coordinates, in our generalized coordinates, this should also be the mechanical power, right? We have angles, we have torques. There are, if we have generalized coordinates, we also have generalized forces. And actually, this is the way we use to define our QJs. So if we have our coordinates, then by means of mechanical power, they are the generalized forces are defined. Likewise with the constraints. There's a bit of a relation to that. Like if we define a constraint, then automatically the Lagrange multiplier or the constraint force is defined. If we take 2 times the constraint, then the Lagrange multiplier is going to have a different value. So that's where the definition lies. And again here for the generalized forces. Now we can express our coordinates in terms of our generalized coordinates. That was the whole goal. We have 2 generalized coordinates by which we can define any configuration. And we call that the coordinate transformation. And how does it go? Well, if you look at the picture again, then it's sort of easy just from the picture to say, oh yeah, x1 is, oh that should be, oh we start from the origin, and then it's L over 2 cosine alpha, and then yeah, you can write alpha, but you can also write Q1. For clarity I now write alpha, but remember this is Q1, the first generalized coordinate. Y1, L over 2 sine alpha, and phi 1, oh that's alpha in itself, right? Then x2 is, well I have to start at the end point here, which is L times cosine alpha plus L over 2 cosine beta. Y2 ditto L over 2 cosine sine beta L over 2 sine beta. And then the angle phi 2 is alpha plus beta, right? So that is your coordinate transformation, which luckily we can write down explicitly here. Yeah, the question from the audience.
Is beta not defined as the angle, not relative to like the x-axis, but plus alpha?
Yeah, alpha is defined as the angle relative between body 2 and body 1. That's how it's defined. And I do that on purpose to show it's a generalized coordinate. It's not some Cartesian coordinate, it's just the thing you cook up.
Yeah, but does that make x2 and y2 incorrect?
Is that incorrect? Yeah, here is something incorrect, right? The first part is okay. Sorry, the first part is okay, right here. But the second part is here wrong. This is wrong. Yeah? I agree. Yeah. Thank you for watching. So then I have to add alpha right here and put brackets. So at least one of you is paying attention. Okay, so we are able to express our center of mass coordinates in our generalized coordinates. If we can do that, we can also express our speeds. If we can write xi is xi of qj, then we can also write our speeds, like x dot I is, yeah, So first we have to differentiate this to the coordinate, and then the coordinate with respect to time. And we have a nice shorthand notation for that, xi comma j times q dot j. And of course this guy is the Jacobian of the coordinate transformation. So that is a Jacobian. Now we are able to connect stuff, because the power in this mechanical system, the power which we have at our center of mass coordinates, that's one way for describing the system, but that should of course be identical to the other way of describing our system, the virtual power for if we use generalized coordinates. The choice of coordinates does not change the amount of virtual power in our system. That should be the same. And now together with that, and that should hold for all, for all, there's only one unique set of coordinates, and that is of course our generalized coordinates. So it should hold for all the generalized speeds which are non-zero. Now via the Jacobian of this coordinate transformation, now we can connect those two. These are real velocities. So for the virtual velocities we can write actually the same. So we get here x I comma j delta x dot j equals qj delta x dot j. And since this holds for all virtual velocities, we get j equations, right? So we get j equations, meaning qj equals xi comma j times fi. So now we see how we can get from our center of mass coordinates, center of mass forces, to our generalized forces. If we know what our coordinate transformation is, we now can find out how we transform the forces at the center of mass to our generalized forces. And as I said before, by defining this mapping, you actually have defined, and through power you have defined these forces, and this is this example. But now we're going to do a trick. Here we're going to substitute our expression which we found from our kinetic and potential energy. So we had this expression, remember, d dt, because finally we want to have equations of motion, dx dot I, plus dv dxi equals fi. So this guy we're now going to substitute in here, because those are the forces expressed in the center of mass coordinate. So what do we get? We get qj equals, and then we have this Jacobian guy which we put in front of him, and let me write it out again, like that. Maybe it makes things a bit more clear. Instead of using the comma notation, I go back to the full notation with the differentials. So then we have a bracket, and then we put in this equation for this one, and there we get d dt with respect to the speeds plus potential energy with respect to the coordinates. Yeah, question.
How do we know that forces are not included already in the potential? Like at the beginning we said that in that equation, force is not included in the potential.
How do you know that? Well, that has to do with how is potential energy defined, and that is defined as this integral of force times distance, and the question is, does such a function exist for all types of forces? And the answer is no. And then we say, that function exists for potential, only for potential forces. And what are they? Well, forces for which we can write a potential. So it looks like a snake which bites itself in the tail, right? But the whole thing is, And it has to do with that you can, if you do the integral over the force over the path, that if you end up at the final point again, that you do not lose energy, and they are defined then, those are as potential type of forces. So how do you know? I think it's well defined in the first part of advanced dynamics, so read all about that. Yeah, it takes too much time now to go into that for now, but you have potential forces, and like dissipative forces, those are not non-potential forces. You cannot put them in a potential. But you can also, if you want to, you can also add other forces here in the equation. But for now, we just keep it like this. The key is that we want to connect our CM, our equations in the CM, to our generalized coordinates. Now we see here that we have this partial derivative here, and then we have derivatives here. And actually, I want to have all derivatives should be with respect to q's and q dots and all those things. So I want to get rid of all the x's. Now I can do that. Yeah, question. Not equal, yeah, I forgot. Thank you, good point. Should not be equal to 0. Okay, I forgot the not. So what you want in this equation here is that you want all the derivatives should not be x like here, but should be q and q dot and so on. And we can do that because we can push that thing into the equation. So again, qj equals, now I'm going to put this one in here. So we get d dt, dx, dqj, dt, dq dot. But by doing that, if you differentiate a times b, you get the differential from a dot times b plus a times b dot. And we only have a times b dot. So we have to subtract a part. And the part we have to subtract is of course the d dt of this Jacobian dxi dqj times this partial derivative. Otherwise we did too much, and then we have our plus dv dxi times our dxi dqj. Well, let's start at the end. Let's begin at the end, and then it's very clear. We can just cross out these two, and we see, oh, it's just the differential of potential energy with respect to our generalized coordinates. That's easy. So that is easily solved. This first part, that's now I only have differential as q. Now we have to focus on these. I want to get rid of the x's here, but that's not so easy to cross out this one against this one, because here we have x dot and here we have xi. Here we have a time derivative and here we have the coordinate itself. So we cannot cross them out. And the second one is, what is the time derivative of a Jacobian? So let's start, as we start at the back, let's start with this one. So what is this? So what is the time derivative of this Jacobian? xi dqj equals, well, just use the definition, right? It's a function of these generalized coordinates, so you have to do xi, and then I have to differentiate, I need another variable, qk, first to the coordinate, and then we have the, it's becoming a mess. It's becoming a mess. First we have to differentiate with respect to our generalized coordinates, and what do we differentiate? This guy, and then we differentiate that guy, this is a k, with respect to time, get q dot k. That's just by definition. Something with respect to time is something with respect to the coordinates, time the coordinates with respect to time. Now, if you look closely to this one, you'll recognize something. If you pull this together, and then we have to pull this together, yeah. This looks a lot like speed. Let me exemplify it. So we have d2 xi dqk dqj q dot k. So now I'm gonna grab this part as one whole, and of course 1d, there has to be 1d, and that is by definition actually x dot I, the thing in the cloud. And then we have 1d left. So the time derivative of a Jacobian is the derivative of the time of these time derivatives. So this is solved, and then we can also cross out this x dot, but we'll do that in a second. So that is the first part. Now this part, what is the dxi dqj? What can we do with that? Well, let's look. Finally, I want something to have with speed, right? So let's look at the definition of speed, xi. That is dxi dqj q dot j. Now, what happens when I take partial derivative of the speeds with respect to the generalized speeds? This is just a, I go up a little bit. So this is just the matrix, the Jacobian. It's linear in these speeds. So if I differentiate this to my qj, I of course get this Jacobian in itself. I get dxi dqj. And we have seen that before. If we have the Jacobian, then the Jacobian of the speeds is the Jacobian in itself. So the Jacobian of the coordinates with respect to each other is identical to the Jacobian of the speeds with each other. So these two I'm going to now substitute here. So I'm going to write qj equals, maybe I copy this, I can do that, that's maybe clearer. So the lasso is on, so I get this guy, I copy it, put it somewhere down here, and this can go away then. Oh, this 2, go away. And we go back to 100%. So now we have resolved a couple of things, so let me repeat this. qj equals, here we get ddt of, I can write dots here. The Jacobian of the coordinates is identical to the Jacobian of the speeds. xi minus this part, the time derivative of this Jacobian is the Jacobian of the time derivative. So that was dx dot I dqj dt dx dot I, and we already resolved this one. qj. Okay, now we can cross out these guys, right? There was a dot here. So these can go away, this can go away, and finally we get qj equals the time derivative of kinetic energy with respect to the generalized speeds minus kinetic energy with respect to the generalized coordinates plus potential energy with respect to the generalized coordinates. And this is what we call the Lagrange equation of motion. Lagrange equations of motion in terms of generalized coordinates. So the only thing we have to do now for a system is to write down what is the kinetic energy of our generalized coordinates and generalized speeds, and what is the potential energy of our generalized coordinates and speeds, and then we take this thing and we just crank the machine. Or, in words of Lagrange, You don't need to make any pictures. The only thing you have to do is algebra, formulate in an algebraic sense the kinetic energy, and in algebraic sense the potential energy, and then by just regular algebra you get your equation of motion. And that sounds, of course, marvelous, right? You can solve any problem, as Lagrange said. Any problem. As long as you can differentiate. And there's even a big advantage, because differentiation is just an algebraic operation too. Like finding a primitive, that's just lookup table. If you have something and you want to know what is the integral, you look in the book and you find the function which, yeah, I have it. But differentiation is just an algebraic operation. It's the limit case of a delta going to something, and then you cross out the small parts and then you have the answer. And indeed, computers can help. Computers can do that differentiation for you. They cannot find integrals. They're very bad at that because it's table lookup. But doing differentials is super simple. I always say differentiating is a one-way street. The moment you have differentiated, you cannot go back. You have no idea what the primitive was. Yeah, if you remember, or if you have a book, but there's no algebraic operation for that. For integrals, no algebraic operation. For differentials, there is. So computers can do that. So your symbolic toolbox in MATLAB can do that. So you can write a script which gives you the equations of motion, as long as you can define what the kinetic and potential energy is. So let's do an example for that. Example. An example is super simple. It's we have a wall here, and we have a cart, a small cart, and then we have a bob here, a mass, and the thing is moving, S, and there's an angle phi, and there's a L, and there's a coordinate system X and Y, and an origin, and I think that's all we need. And now, of course, the generalized, the mass coordinates are, of course, X and Y of the bob here. That's the only thing. And but I want to use generalized coordinates, and although it doesn't really look like helpful here, I mean, we have two center of mass coordinates and also two generalized coordinates, so that's not very helpful. On the other hand, well, it's generalized coordinates, it's another system, and it sort of nicely demonstrates how the thing works. Okay, we have our coordinates, we have our speeds then, of course. So kinetic energy was defined as this guy, right? X dot mij x dot j. And what is the mass matrix in our case? Mij is just mass, 0, 0 mass, right? That's super simple. Fi, did we have applied forces? Yeah, we have gravity. Yo. So mg. So we have a 0 and minus mg here. Those are our applied forces. We have our generalized forces. Then we have to find that mapping, of course, for how do we map our coordinates to our generalized coordinates. So x is s plus L sine phi, y is minus L cosine phi, something like that. Yeah. Then we can do the speeds, right? X dot and y dot. X dot is s dot plus L phi dot cosine phi, and this is L phi dot sine phi. Well, the kinetic energy, as we have defined here, of course, is 1/2 x dot squared plus y dot squared, right? Then we substitute these guys in there, and then we get our kinetic energy, 1/2 m times, so x dot is s dot squared plus 2 s dot L phi dot cosine phi plus L phi dot squared cosine squared phi plus L squared phi dot squared sine squared. These I can take together as L squared phi dot squared. Yeah. So I end up with kinetic energy is 1/2 m s dot squared plus 2 s dot l phi dot cosine phi plus l squared phi dot squared. How about potential energy? So let's put the force, this is really a potential energy force in a gravitational field. So the potential energy is, well, just simply mgh. And actually now I'm done. Yeah, you have to do the algebra, but that is sort of peanuts, right? So what was the equation of motion? Time derivative of kinetic energy with respect to the speeds minus kinetic energy with respect to the coordinates plus potential energy with coordinates is these generalized forces. So if these are all the elements, then we just have to, we have two equations, so J is 1, 2, 2. Let's start with this first part. So we have the dt ds dot equals, and then we have to look at our equation, of course. Well, to s dot, then we get ms dot. That is nice. The half and this 2 also go away. It looks like coincidence, right? Well, anyway. Plus L phi dot cosine phi. More s dots? No. Then we have the other one, that's dt d phi dot. Is here's a phi dot, but the 2 goes away with this half. Life is very special. M s dot, oh, I miss an m here, of course. M s dot L, because I do with phi dot cosine phi. And then of course for this guy I get, this 2 goes to that half again, so m L squared phi dot. Plus m L squared phi dot. Okay. What else? Oh yeah, then we also have to do these guys. And this of course we have to do with respect to time. Oh, let's do that again. So now we have to do this with time, so we get the dt of this guy is ms double dot plus ml phi double dot cosine phi plus, oh, it's a minus, by the way, minus ml phi dot squared sine phi, right? Yeah. With respect to time. So, and then the other one, this with respect to time is m s double dot l cosine phi plus m l squared phi double dot minus also m s dot l phi dot sine phi. Okay, what else? Oh, to the coordinates. So the dt to s is, there is no s, right? There is no s in the kinetic energy, so that's 0. Dt to phi, yeah, there is an angle phi. That's this part, cosine phi. And again the 2 goes away, so I get m s dot L phi dot sine phi, right? And is there a minus? Yeah, there's a minus, I guess, from the cosine. Now other phi's. Okay, now the potential energy. Well, that was easy, mgh, but h was actually mg, and the height was 1 minus L cosine phi, right? Because everything has to be defined in our generalized coordinates. And the height of the bulb. So the potential energy with respect to s, well, there is no s in the equation, so that's 0. And the potential energy with respect to our coordinate phi is minus becomes plus, so we get mgl sine phi. Now we have all the balls, all the ingredients, so we put everything together with the right pluses and minuses. And if we do that, then, well, we can already see it. Let's just talk about it and then form our equation. So finally, I should end up in this. No Lagrange multipliers, right? S double dot, phi double dot equals, and then on the right hand side, forces. Okie doke. So let's first take all the S things. Then I get the first equation. All the S things. So all the S parts from this. MS double dot. I got you. ML cosinus V phi double dot. So ML cosinus phi. Yeah. Then I have minus ML phi dot squared sine phi. So that becomes here ML squared phi dot sine phi. Right? What else? Then I have to subtract the kinetic energy to the coordinate. Where are you? Oh, that's 0. Not there. No term. So then I have to add this guy, potential energy with respect to S. There's also nothing. Yeah. So that's done. And then we're done with all the S's. That was our first equation. Second equation. Everything with a phi double dot. So here we go. I have to start with the S double dot. Oh, I get ML cosine phi. Hey, I already got that here. Okay. And then ML squared. Yeah. What else? Oh, I have this term. Yeah. So I get M S dot L phi dot sine phi. That's this guy. And then I have to subtract that one. Oh, minus ms dot L phi dot sine phi. Okay. So these just go away, right? From these two terms, this guy and this guy, they just cancel each other out. Maybe I made an error, who knows? Then kinetic energy, potential energy, so plus to the other side, so we get minus mgl sine phi. And then that's it. So finally, my equations of motion become, well, this is the same, ml cosine phi, ml cosine phi, ml squared, s double dot, phi double dot, on the right hand side, ml squared, phi dot squared, should be a square, sorry, sine phi minus mgl. If I look at it, I'm sort of happy. Why am I happy? Because it's time? Yeah, could be. Because of the clock? The clock? No, not of the clock. Yeah. Oh, yeah, you can say plus a torque Ts and here plus a force Ts and a torque T phi. You can add them, yeah. So, good point. Yeah, then you have the pendulum equation, but that was not my happiness. My happiness was something else. You cannot read my mind. What? Yeah, that these cancel out. I sort of expected that because we did too much work. But look at the mass matrix. Yeah. It's symmetric, yeah. That's cool. And I love symmetric things, so therefore I'm happy. Can we always solve the system? Is there always a solution? How do we check? Yeah, but there's no time left, so we have to do that next week. Yeah?